Hey guys, today we will continue in our series where we go through the courses in FPGA Academy. This is a design that we'll try to implement today. This design is part of Lab 2, Numbers and Displays. In the last episode, we finished Lab 1. You can watch Lab 1 on my YouTube channel. And we will use some of the code that we have developed in the previous part in today's project. So let's start with Lab 2. This is an exercise in designing combinational circuits that can perform binary to decimal number conversions and binary coded decimal BCD addition. We wish to display on the 7-segment displays, hex 1 and hex 2, the values set by the switches 7 to 0. Let the values denoted by switch 7 to 4 and switch 3 to 0 be displayed on hex 1 and hex 2 respectively. Your circuit should be able to display the digits from 0 to 9 and should treat the valuations above 10 as don't cares. Create a new project which will be used to implement the desired circuit on your Intel FPGA series board. The intent of this exercise is to manually derive the logic functions needed for the 7-segment displays. Therefore, you should use only simple VHDL assignment statements in your code and specify each logic function as a Boolean expressions. Okay, I have already made a quarters project for this for part 1. So we want to, I'll close these, and we want to first implement a VHDL entity that will take switches and show them on the hex 7-segment display. So that's what we will do now. So let's create a VHDL file. Let's insert template, VHDL user entity, insert, close. And we have inserted here. I don't want to do that. And we will call this number 7-segment display. And as input we will take number, binary number. It will be std logic vector 3 down to 0. And we will take, and as output we will have hex, and it will be std logic vector 0 to 6. We will save it as 7-segment display. And let's create the architecture. So we want with bin number, select hex, and with select when. So when, and there will be binary number here and binary. So we select some output when we get some binary number. So these will be from 0 to, the binary numbers will be from 0 to 9. So we have to create this 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then others. That's for the don't cares above 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we want to select the appropriate part of the 7-segment display, the appropriate segment. So for example, for 0, we want to select all except for 6. So we want to, and selecting means driving it down to 0. So if we want to turn it off, we want to drive it to 1. So which means we want 6 times 0, 1, 2, 3, 4, 5, 6, and 1. So we will drive segment 0 to 6 to be on, and the last one to be off. So for 1 we will turn on 1 and 2. So it will be 1 and 2, and then once, like this. For 2 it will be all except for 2 and 5. 2 and 5, so 2, 5. For 3 it will be 4 and 5. 4 and 5, so 4 and 5. Then we have 4. 4 will be 0, 3, and 4. 0, 3, and 4, like this. 0, 3, and 4. Yes. Then we have 5. That's 1 and 4. 1 and 4, like this. Then we have 6. That will be just 1 off. So 1. This is 6. 7 will be 0, 1, 2. 0, 1, 2, and all the others off. 8 will be all of them on, so that's just zeros. 9, that's 4 off, so 0, 1, 2, 3, on, off, and like this. And others, if it's invalid, we will display dash, so that means it's reverse to 0, so that will be ones and 0. Only 6th segment will be on. Okay, this seems fine. So let's test it out. So we will have switches and inputs. And it will be 9 down to 0. Then we will have hex 0, out, std, logic, vector 0 to 6. And we will copy this one more. And this will be 1. And then we create the logic. So we will import the component number 7 segment display. We will import the ports like this, and component, and we will create instance of this component. We will call it sec0 instance of this port map, and we will map the ports. So inputs will be switch 7 down to 4, and it will show on hex 1. And we will create another instance. There will be this instance will be segment 1, and it will display this switches 3 to 0 and display them on hex 0. Hex 0. Okay, let's test it out. And we don't have set top level hierarchy, so set this as top level hierarchy, and now it seems fine. Do we have any syntax errors? No. Okay, so let's see if it works. We will program this. Select the output. We don't have output files yet. We have our We have to wait for the compilation to finish. And now we can select our output file, program, and we can see. So you can see that we have, right now we have all zeros, and I can switch 11 to, let's see, 4, 5, 6, 7, let's see, 8, and 9. And if I put anything above, it shows dash. So this seems to be correct. I'll try something like 40. Let's try to display 49. And I can show 49 on the 7-segment displays. So this is correct, and we can continue to part 2. And we can continue to part 2. You are to design a circuit that converts a 4-bit binary number into its 2-digit decimal equivalent. Table 1 shows the required output values. So we will have 4-bit binary number that goes from 0 to 15 with 16 numbers. We can show values from 0 to 15, and we want to convert them to their decimal equivalent. The output Z for the N, of course, we will do the design that we have seen in the beginning. We will have our input, we will have multiplexer, comparator, and circuit A, and our 2 7-segment displays. When the number is less than 0, comparator will set Z to 0. So comparator can set Z to 1 or 0 if it's bigger or lower. If it's more or less. And if it's 0, we select the input number in this multiplexer. So on this 7-segment display, we will display the input number, and on this we will display the 0. And if it's bigger than 9, which means 10, so it's 2 digits, this selector will be set to 1, which means on the 7-segment display we will display 1, and the multiplexer will select the other input, and that will be from the circuit A. So what we want is, if we have, for example, input 1010, which is decimal 10, we want A to output all zeros. If we have 11, we want to output 1, and so on. So that's what we will do now. Let's read the steps. Write VHDL code to implement your design. The code should have the 4-bit input switch 3 to 0, which should be used to provide the binary number, and the 2 7-bit outputs to show the values of decimal digits. The intent of this exercise is to use simple VHDL assignment statements to specify the required logic functions using Boolean expressions. Your VHDL code should not include any if-else case or similar statements. So we have to only use Boolean expressions. Let's start creating these. So first we will create circuit A. So let's make a new VHDL. We will insert the, not this. We will insert a template. I'll just copy this. So we will call it circuit A, and as input we will take binary number in std logic vector and it will be 3 down to 0. And as output, we will have, let's call it A out, std, and it will be the same as here. Let's save it as circuit A, and so let's look at the binary numbers. We are only allowed to use Boolean expressions, Boolean algebra. So if we look at, basically what we want is from 11 to get 1, from 12 to get 2. So if we compare 11, which is 1011, and 1, which is 0001, we can see that the first digit, or the 0 bit, is always the same. Here it's the same. So we can assign the output bin number, and we can assign the last bit. The second bit, if we look here, it's 0, here it's 1, 0, 0, 1, 1, 0, 1. It's always inverse. So it's always inverse to the first bit. And it's also inverse to the last bit. So I'll put not here and not here. And we'll have to make this. You can see that there is 1 and there is always 0 here. So it's always inverse, the fourth bit. And the third bit is a little bit trickier, but it's not that hard. If we look at it, we can see that for example here, if we have let's think about it a little bit. If we have one yes, so if we have 1 here, we select the second bit for the third bit. So for example here we have 1 here, so we select this once. Here we have 1 here, so we select zeros. Here we have 0, which means we select 0 for the third bit. So I will write it so you can maybe understand it better. But what we will do is it will be 3 and 3 and 2. So it will be and 2. No, this will be 3. This will be 2, and this will be 1. So you will just take the product of and third bit and let's say the second bit and first bit. We will take the and product. So here it's 1, here it's 1, here it's 0, here it's 0, and here it's also 0. And this will hopefully give us the correct solution. But to see if it's correct, we will use, because in the steps they want us to use simulator to test it out, compile the circuit, and use functional simulation to verify. So we will verify now if it's if our design is correct. We will create a university program waveform, and we will save it. Then we will set the end time to 20 nanoseconds, for example. Then we will and we have to set the circuit A as top level entity and do analysis and synthesis. We don't have to compile the whole project. We don't have to do the fitting and timing analysis and so on. And we have yeah, we have to put this here as well. Let's see if we have any errors. Okay, now we can go to the simulation and we will go to insert node finder. We will, and we can see we have our inputs and outputs here. We will select them all and import them. And this is our input. Then I have to do we have to do this. And I have to do FPGA digital logic get. I have to change code here because Quartus. I have a new version of Questa, and the Quartus is this script is for older Questa version, so I have to change the script here. I have to insert this, and now we can run it. So let's try it out. Oh, and before we do that, we should count value. We will count every nanosecond. So now we have every nanosecond the input increases. Now we can run the simulation. Okay, and we can look at if we have correct. So you can see that our inputs increase every nanosecond, and as output we want, let's do this for the output to do. As output, we don't care about these numbers because until 9 this doesn't get selected, but if it's above 9 and less than 15 or less than 16, we care about these, and we can see 1, 0, 2, 3, 4, 5. So it corresponds to 10, we want just the 0, 11, we want just the 1. So this seems to be correct. That's great. We successfully simulated our circuit A, and we will continue with comparator. So let's create a new file, FPGA file. Let's copy this. We will create compar 9. And this will take as input binary number, and it will output Z, and it will be just std logic. It will be a Boolean value, 0 or 1, if it's bigger or smaller. And we don't need this. We don't need this. And here it will be Z. Again, if you look at numbers, if we look at the numbers that are higher, that are bigger than 9, for example 10, 11, we can see that the first bit has to be set for number to be bigger, and also the first and the second bit, the first or the second bit has to be set. So the number is bigger than 9 if the most significant bit and the first bit are set to 1, or if the most significant bit and the second most significant bit are set to 1. So we will try to implement this in VHDL. So bin num3, the most significant bit, and 2 or, and we'll do parentheses here, and or 3 and 1, and save it as compa9. And we can again test it in simulator. So we'll run the analysis and synthesis. This is correct. So we can run the waveform. I will have to again do this. I'll copy the part of the script, change it here, save, and we delete this and insert node. Maybe we have to create a new one. Do I want now? And we create a new one. Waveform. Save as. Let's call it waveform 1. Now we will set the end time. We will put 20 again, nanoseconds, and we will insert the nodes as done. And oh yeah, I don't have to create a new waveform probably. I just have to set the comparator as top level entity. And now run the analysis and synthesis. We can try now. Okay, and we have our inputs and outputs from our comparator 9. What do we... Okay, let's try to create a new one. So there is no... Save it. 20 nanoseconds. Now we insert the nodes. Okay. The following errors were found. Invalid node name. Invalid node name. I didn't select them. Okay, now. Oh yeah. So there was the error, and we reset. This seems fine. This seems fine, and change this. Like this. Save. We will also do the count from every nanosecond and try it out. And if we put again, you can see from 0 to 9, the output value is 0, and above 9 and below 15, the value is 1. So this design is correct as well. We have successfully tested circuit A and comparator 9. And the final is the MOOCs. So let's copy this to a new VHDL file. 4-bit. We will take 4-bit inputs and 4-bit out, and we will have 4-bit output. And we will call this Z. Again, here 4. We'll call this Z. And this is all we have to do. MOOCs 4-bit 2 to 1. And now we can put it all together. So let's create a new VHDL file. Let's copy part 1 to this file. Call it part 2. Save it. And we need to import all the components. Component and component. We will have to import 3 in total. So and we will import this component. We will import this. And we will also import, we have comparator, MUX, 7-segment display, and we need circuit A. Let's delete this. So we have our instances of these blocks, but we need one multiplexer, one comparator, and one circuit. Let's create comparator. It will be comparator port map, and it will, as input, it will have switch 3 to 0, which is our binary number, and as output it will be Z signal. We have to create this signal, so we will create Z signal, and it, or we will create signal, and it will be std logic. Then we want to create our circuit A. So let's create circuit A inst. It will be circuit A port map, and as input it will also take switches, and as output it will be a signal. Let's call it A signal. So A signal and Z signal, those they are, this is Z signal, that's just wire, and this is A signal, and this is A signal. And as you can see, A signal is 4 bits, so we have to change this to vector 3 down to 0. Okay, and finally our MUX instance, and it will be instance of this MUX, and it will take as an input Z signal for select. If it's 0, then it will take switch. If it's not, then it will take A signal, and it will output MUX out, or MUX signal, or let's call it MUX out. MUX out, and MUX out will be also MUX out. It will be also 4-bit. And then we have our, so this is the 0 hex, and that will take the MUX out as input, and our second will take the Z signal as input. But since Z signal is 1 bit and this takes 4 bits as input, we will end it, we will add just 3 zeros to it. So it will be 3 zeros and Z signal. Okay. Let's try to compile, or we have to first set it as top level entity. And now we can compile. And I think this could work. Okay, analysis is fine. So we'll test it out. Use function simulation, we have done that. Download the circuit, test the circuit by trying all possible values of the binary number and observing the output delays, displays. We'll do that. Okay, let's program. We have to auto detect and select the output. Program. Okay. So let's try all possible combinations. So we have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 6, 0, 7, then 8, 9, 10, 11, 12, 13, 14, and 15. And that's the highest number we can go. So it seems to work correctly. So we have finished part 2. We have finished this design. We can also look at RTL viewer to see our design. Let's look at RTL viewer. Yes. Or maybe this might be better, technology map. Oh, let's look at the RTL viewer. We can see our MOOCs, then we can see our, this is our comparator, this is our AA circuit. Then we have MOOCs has inputs from our binary number and from our circuit A, and comparator outputs Z as select for the MOOCs and also as input for the display. So we can see that we created this design in our Quartus VHDL. So we have finished part 2, and we will look at part 3. We will do this in the next video, but let's just look at it. We will implement the full adder, and we will implement this circuit, and yeah. So that's for next video. We will do this in the next video. So make sure to subscribe if you want to see this, and I'll see you in the next video. Bye.